All right, we're going to continue to look at integration by parts. We got a few more examples of the technique by parts can be used to help us integrate pretty complex expressions. The next type of integral sometimes goes by this name. It's called a wraparound integral. And you'll see why I got that name in a second. So let's say that I gave you this to integrate. Let's go e to the 2x sine x dx. All right, so again, you go through all your questions. Can I integrate it directly? U substitution, so on and so forth. By parts should be jumping out at you because we have two different types of functions, right? We have an exponential and a trig function. So maybe we could do it that way. Well, we can, but let's get started with our by parts. If we say u equals, now remember in the last video on by parts I told you, you want to pick u to be the function that goes away when you start taking its derivatives. However, if you take a look at e to the 2x, that thing, that's supposed to be an x, e to the 2x, that never goes away when you start taking derivatives, right? You always get e to the 2x back, so that's not going to work. Grab an eraser. What about sine? Sine's not going to work either, right, as far as going away, right? You start out with sine, you start taking the derivatives, it just bounces back and forth between sine and cosine. So neither one of these functions are going to go away, if we pick it to be our u piece. So actually, this is one of the few ones that I'm going to tell you, let's take a look at the dv piece first. I know of these two functions, one I'm going to have to take the derivative of, one I'm going to have to integrate. One of these you're going to be better at integrating than the other. And most of the time, it's the exponential. I find that a lot of calculus students get their sign mistakes when they try to integrate sines and cosines, but they can do the derivative just fine. Actually, here's the big thing. It doesn't matter. Either one here will work. You'll get the exact same answer. All right. So let's put our pieces together. So du would be cosine x dx. V here would be 1/2 e to the 2x. All right, so our original integral is equal to uv, so 1/2 e to the 2x sine x minus the integral of v du cosine x dx. Now just for looks, I'm going to go ahead and pull out that 1/2, so we get e to the 2x cosine x dx. All right, so now we still have another integral to do, and it's quite a bit like our first one, right? We have an exponential times a trig function. So you say, okay, let's try by parts again. Now, in this time, you do not have a choice of what you pick to be u and what is dv. Since originally you picked u to be the trig function, it has to stay the trig function. So this is going to be cosine x, and dv is e to the 2x dx. So du is negative sine x dx, and v is 1/2 e to the 2x. All right, we need to move this up top here. So far we have that this is equal to 1/2 e to the 2x sine x minus 1/2. Now, we're about to break this integral up into two pieces, so this negative 1/2 applies to all of that. So we get uv, so 1/2 e to the 2x cosine x minus the integral of v du. Now, I'm going to kind of skip a step here just for board's sake. What's our constant? Our constant is a negative 1/2. So if I pull out a negative 1/2, that's minus negative 1/2 e to the negative 2x sine x dx. All right, so uv minus the integral of v du, but our v du piece was minus, that's why it became a plus. So I'm going to do one more step here again to kind of clean this up. I'm going to distribute that negative 1/2, so that's e to the 2x sine x minus 1/4 e to the 2x cosine x minus 1/4 integral e to the 2x sine x dx. Okay, so the idea for by parts is now we should be able to do this integral here. But you're like, well, hold on. that's the same integral I started with. So basically I've done a lot of work and didn't make it anywhere. But you actually have, because this is why it's called a wraparound integral. By doing by parts a couple of times, we managed to wrap back around to the integral we started with. Now here's where laziness kind of hurts a lot of students. And by the way, I've been lazy since the very first video on this as well. I've just been writing equal signs as we've gone through doing by parts all the way down. But remember, this is what's on the other side of the equal sign, right? This equals all of these. So on this side, I actually have the integral of e to the 2x sine x dx. Which means I have an equation with the thing I'm trying to solve for. So all I got to do is move this to the other side, combining like terms, and I should be able to solve for what I need. So watch, I'm going to add that to both sides. So I have e to the 2x sine x dx plus 1/4 integral e to the 2x sine x dx equals 1/2 e to the 2x sine x minus 1/4 e to the 2x cosine x. Now these are like terms, right? Here I have 1 and here I have 1/4, so 1 and 1/4 would give me 5/4 e to the 2x sine x dx, 1/2 e to the 2x sine x, 1/4 e to the 2x cosine x. All right, so if I want to know what this integral equals, all I have to do is just multiply both sides by 4/5. So the integral of e to the 2x sine x dx will be 4/5 times 1/2 e to the 2x sine x minus 4/5 times 1/4 e to the 2x cosine x. And I'm just going to go ahead and be a little bit lazy here. So what's this going to cancel? That's 1/10 e to the 2x sine x minus, let's see, the 4's cancel, so 1/5 e to the 2x cosine x. So there you go, that's what our integral equals. Now that we're completely done integrating, let's go ahead and slap on our integration constant, and there we go. So wraparound integrals, pretty messy, they really are, but they happen quite a bit. So make sure that you know how to do these. The idea for a wraparound integral is once you start doing by parts, you end up with the exact same integral that we started with. So in this case, right, we started with the integral of e to the 2x sine x, and by doing by parts, we got back to the exact same integral. If that happens, all you gotta do is move that integral to the other side, combine your like terms, and then solve for the integral that you're actually trying to do. All right, so very, very helpful with these wraparound integrals. Like I said, they do show up quite a bit. All right, let's take a look at another technique. We actually already know how to do the problem I'm getting ready to put up here, but I'm going to show you somewhat of a quicker way to do it. This is called the tabular method. The tabular method is a quicker way to do by parts in very specific circumstances. Now, I don't like showing students shortcuts, so to speak, but this one is most definitely worth learning just because it is so fast for specific types of integrals. So here, if we have the integral of, let's say, like x to the 4th e to the 2x. All right, by looking at this, you'd say, okay, we have two different types of functions, polynomial times an exponential, and we saw from the last lecture, by parts works really well on this. But notice that we always have to do the same number of by parts as the power on the polynomial. So we'd have to do by parts 4 times for this. All right, so if you have a polynomial times a exponential times sine or cosine or times sinh or cosh, this method works very, very well. And here's what we're going to do. It's called the tabular method because we're going to make a table. Okay, you'll see how many rows you need here in a second. The first one is a sign column, S-I-G-N. The next column is a derivative column, and the third column is the integration column. For the sign column always works exactly the same way. It always starts out as plus, and then you're going to alternate signs, plus, minus, plus, minus, plus, minus, and go down for several. You'll kind of get the hang of it, how many you need after a while, but just kind of go down a few. Now the derivative, you're going to pick the function you would always let be your u. So that would be our polynomial here. So I'm going to put x to the fourth here. So I get x to the fourth. Then start taking derivatives. 4x to the third, 12x squared, 24x, 24, and 0. And go down till you get a 0. That's why the polynomial works really well for this, because we know that the derivative is eventually going to give us a 0. All right, everything else is what you're going to integrate. So I'm going to be integrating e to the 2x. So each time I integrate, I get a 1/2 out front. So that's 1/4 e to the 2x, 1/8 e to the 2x, 1/16 e to the 2x, and 1/32 e to the 2x. Okay, and again, you go down to the 0 shows up. All right, now believe it or not, when you're looking at this, you're like, well, that's a mess. But you're actually done. All you have to do is put all the pieces together. So this integral is equal to. Now to find each term in your answer, where'd my red pen go? All you have to do is across and then down. So for the first term, we're going to do plus times x to the fourth times 1/2 e to the 2x. So the first term is going to be plus times that, so that's going to give me 1/2 x to the fourth e to the 2x. The next term, we go across and then down, so it's going to be negative times that times that. So that's going to give me negative 4 times 1/4 x cubed e to the 2x. All right, and we keep going down till we get to a 0. So it's going to be times that. So it's going to be plus 12 times 1/8 x squared e to the 2x. You see this one's going to be kind of long. This times that, so it's going to be minus 24 times 1/16 x e to the 2x. And let's see, after that, that's going to be plus to there, so we're going to get plus 24 times 1/32 e to the 2x. Now notice, everything after that would be 0, right? Because as we go across, all the rest of those are zeros. So that, other than a little bit of simplifying, is our answer. All right, so let's just go ahead and see if we can manage. Let's see, it's 1/2 x to the fourth e to the 2x. Minus, let's see, the 4's reduced here, so x cubed e to the 2x. Plus 4 will go in each one of those, 3/2 x squared e to the 2x. Minus 8 will go into those, 3/2 x e to the 2x. Plus, let's see, 3/4. Let me check that arithmetic. Let me check the arithmetic on that 3/4. All right, and there you go. So I know it's a really long answer, and it looked like it took us a long time, but imagine having to do by parts 4 times on this, and then putting all the pieces together. So the tabular method is an incredibly quick way to do integration by parts, but generally what you're looking for the tabular method is generally, not always, but generally a polynomial times either an exponential, sine or cosine, or essential cosh. So keep an eye out for this. It is something worth practicing because it can really save you a lot of time.